write to it or you read to it or anything. So you have this untrusted pointer passed in parameter to a C4. You validate the data that is there, but you never test the value of the data. You validate that the pointer is valid, but you don't check for the values pointed by that pointer. So basically, you can have, like in that particular example, you have an addition of multiplication. So if all the fields are 0, the total size is only 0. So sticky data is 0. Then you call the internal function of the kernel as last parameter 0, which is here. And then you have the allocation of 0. So you have a particular flag that is user controlled. So you can enter this condition. And then you have a dangling pointer because the 0 located pointer is using arithmetic. And so you store a dangling pointer basically in a kernel structure. And then you have the RTL copy memory. The thing is, the RTL copy memory is like memcopy in the Windows kernel. So when you do a memcopy of 0 bytes, nothing happens, so there is no bug. However, the dangling pointer is still stored in a kernel structure. So when you just look at the code of that C4, nothing happens. Like there is like a 0 location, and you copy 0 bytes. There is no vulnerability. However, there is no dangling pointer in one of the kernel structures. And if you look at another C4, you can see that all C4 use the same structure. They can look up the same structure, and then they can dereference the pointer that was stored. So basically, you cannot just find a bug by analyzing one C4. You can see like one C4 is giving a dangling pointer, and another C4 is reusing the pointer, and this is going to trigger a vulnerability. So you cannot just analyze function per function because then buffer overflow, you can find all buffer overflows like that. You actually have to check if those particular dangling pointers are reused in other C4s that are the entry points of the kernel. So in that particular example, the same handle is looked up, the same flag is tested, and then the same pointer is dereferenced. So in one C4, you have the dangling pointer, and another C4 that is related, you're going to have a dereference of the dangling pointer, which can go beyond the data that was allocated. So in this particular example, it's just on the right-hand side of the expression here. So there is no call execution possible. It's just invalid dereference. So this is denial of service only bug in this particular instance, obviously. But I'm going to detail some other examples where it was much more serious. So as I said, when you have a 0 location, you don't systematically have a security problem, or you even don't systematically have an issue at all. Sometimes if you just allocate 0 and copy 0 bytes inside, nothing happens, so that's cool. However, when the problem happens, sometimes code execution is not possible, and sometimes code execution is possible. So we're going to give a couple examples where code execution is possible. Some local and some remote. So this is pretty bad. But again, don't panic because it's just standard behavior. So if you know how to code, normally you're not exposed. Second example. This time we have an example where a heap overflow happens. So not only you have a 0 location, but also data is reaching out of bounds on the heap. So you can actually override the heap on a 0 located chunk. So second example, again, you read a value, probe and read ULONG, which is validation API of the Windows kernel. So you take this parameter, you validate 4 bytes, a ULONG at this particular address, And so this returns the value on 32 bits. And you add to that value plus 1. The thing is, you can have an integer overflow. So if you don't validate that the value you've read from userland is not the maximum value, the fact that you do a plus 1 can make it drop to 0. And straight away after that, you have an allocation of that size. So again, you have a 0 allocation, which is valid. It returns a valid pointer. So the fact that you test for 0, and this is even removed from the log, I shouldn't have made it. But every allocation is tested for null after that. So it's not going to forbid any kind of exploitation because allocating 0 bytes does not return null. So if you do malloc 0, it returns a valid pointer, or user alloc pool of 0, it returns a valid pointer. Straight, you can copy memory, but copying 0 bytes is fine. But then you pass the pointer to an internal structure, an internal function of the kernel. So this algebra is the 0 located pointer. And then you just use the data as it was said, like basically you're going to compute another size, do another location with uninitialized data because you don't know what's after that in the heap. So you do lots of kind of operation. You do mem copy of uninitialized size, so that's bad, obviously. You copy, like you assume that you have at least 1 byte, you copy a null byte. So here buffer overflow can happen in the kernel because of a 0 location. So this is like an example of escalation of privilege bug we have fixed in the Windows kernel. We have a couple. I'm just going to present a few of them. So I'm going to talk about how to find transpose entirely automatically. Do we have any question about what is the 0 locations so far? Clear? All clear?
Question?
Yes.
Have you looked in